Okay, so in the last class we were looking at this diagram, which occurs at second order in perturbation theory, where we considered the lambda perfect theory, and we were looking at this scattering amplitude. We were looking at the second order term, and at the second order in the perturbation theory, the coupling constant from the various contractions in the weak expansion, you can get a Feynman diagram or a process of this form. It basically tells you that the particle comes in from here. So in the scattering process, so you have something like this. The particle with momentum p comes and it goes out with momentum q, and that can be written in this form, just comes in and goes out, and there are correction terms in first order in perturbation theory. So in first order in perturbation theory, you can have a term like this. So this is the diagram which arises at first order in perturbation theory. So you have P, you have Q, you have group momentum K, and then there are, so this is the first order correction term, and then you have second order correction terms. And one of the terms that appears at the second order is of this form, where the particle distribution comes like this. There are two vertices. So the fact that there are two vertices, it indicates that this is a second order term, but there can be many second order terms, because you can also have a term like this. You can have terms like this and so on. So this is one of the terms at second order, and we were trying to write down a mathematical expression for this, and we had actually derived a mathematical expression for this from the Week's theorem of the weak expansion. And then, since we had already derived the Feynman rules from the diagram that arose at first order in perturbation theory, from here we derived the Feynman rules. So in the previous, in the last class, what we were trying to do is the expression that we derived here from the Week's theorem, we were trying to just write down that expression simply by applying the Feynman rules. Let us do it once again. So this is the diagram that I've written in this way. If you write this and just rotate it like this just tells you that the direction of flow of time is like in this direction, from the bottom to the top, and here the direction of flow of time is from the left to the right. Okay. So this is the diagram that we were talking about, and we have actually derived the Feynman rules, so you can straight away write down the expression for this, the expression corresponding to this diagram. Since there are two vertices, therefore you have a factor of minus lambda each for the two vertices, so that gives you a factor of 2 square divided by the symmetry factor. The symmetry factor, you know that these are the pair of vertices connected by n propagators, gives you a factor of n factorial. Therefore, there are 3 propagators here. Here there are 3 propagators, 1, 2, and 3 internal lines. Therefore, this gives you a factor of 3 factorial. Therefore, the symmetry factor corresponding to this diagram is 6. This is a number, as I told you, this is a number that can arise from the number of ways in which you can contract to get a particular diagram. So you get a factor of 6. Then there are 2 vertices. So corresponding to each vertex, you have a integration over the vertex. So you have 2 integrations now because of these 2 vertices. So this is also a part of the Feynman rule. Now you have these external lines. So this is momentum P, this is momentum Q. So corresponding to these external lines, we will get a factor of 2 to the power of I, Q dot Y, Q to the power of minus I, Q dot W. So these are the factors that you get due to the external lines, which are there in this diagram. You can actually attach a factor of NQ also over here. So it depends on how you choose the normalization factor. It depends on that. If your state gates are normalized in a particular way, then you can get this factor. So you will basically get these factors if you tell that my ket P is basically A dagger P get 0. So if you use this normalization, then you will get these factors. But if you put in a factor of NP inverse here and define it like this, then these NP factors will get cancelled. So it depends on how you choose the normalization. So this corresponds to these external lines. And now you have three propagators. So you have I delta F, Y minus W times delta F, Y minus W. And this is it. So this is the expression in the position space. Just apply the Feynman rules in position space and you will get mathematical expression corresponding to this diagram that we actually derived rigorously from the Fick's theorem, from the contraction procedure. Now, today what we shall do is write this full expression that we have written down here in the momentum space. So, what we will have is the following. And keeping the factors of NQ and NP, this. Now, I write down these factors, make Fourier transforms of this. So this corresponds to this one, and then we have I. So what we have done is we have written down Fourier transforms of these propagators. Let us go to the other side. Can you see the board? Can you see the board?
Yes, sir.
Okay. So now what you have is this. You can pull out the factors of NP and NQ. Then we have times before T2 So we have just written down the momentum integrals, the integrals over this k1, k2, k3, and now we have the integral over d4y and d4w. So d4w, what we can do is following. D4w, just collect the terms which involves w's. So we have e to the power of minus I. So that comes from this term. So p, and then you have w in each other term. P plus, so this will be minus k1 minus k2 dot w. Another term plus minus k3 dot w. So this is the integral involving w. Then we have finally the integral involving y, and that gives us I q minus m. Is this clear? So what we have done is we have separated out the integrals over w, the special integrals, and you can see that this gives you nice Dirac delta functions. So from here we will get 2 pi whole 4 delta 4 q minus k1. See, so this is what we should get from here. And from here also we will get a Dirac delta function. So this will give us finally. So I'll just the whole board. You can see it now. Can you see the whole board? So therefore, so if you perform the integrals over y and w, you get minus lambda square by 6 np nq. So one of the 2 pi whole to the power of 4 will get cancelled. So there are 2 pi whole to the power of 4 factors. So it will cancel 2 of the factors in the denominators that comes in the momentum integrals. So therefore what we'll have is 2 pi whole to the power of 4, and you can write as delta 4 q minus p. Okay? Then we have d4 1 I by q1 square d4 k1, d4 k2, d4 k3, I we have built a function data 4 and what we have here is the following minus k1. Is this clear? So this is after simplification what we will get is the following. Is this clear?
Sir, the 2 pi to the power 4, shouldn't it be in the denominator?
Okay, I'll explain. Can you see the full board now?
Yes, sir.
Okay. See, these two Dirac delta functions gives you a factor of 2 pi whole to the power of 4 and 2 pi whole to the power of 4. Okay. I think you just check 3. You are correct. What will happen is 2 pi whole 4. Let me keep this over here. You have two factors of 2 pi to the power of 4 over here. So that will bring in factor of 2 pi whole to the power of 4 downstairs. So you are correct. So let me just divide this by 2 pi whole to the power of 4 by 8. Now is it correct?
Yes, sir.
Now, as you say, that we will have a 2 pi whole to the power of 4 in the denominator. That is what you get. Because you have it in the numerator to the power of 4 and in the denominator to the power of 8. So you have a 2 pi to the power of 4 in the denominator. And what we have done is we have performed these integrations to get the Dirac delta function, and from these two Dirac delta functions, we have actually replaced in one of the Dirac delta function, we have replaced k1, k2, k1 plus k2 plus k3 by p. So if you do that, then you will get this factor delta 4 q minus p. So you can see that still there are two Dirac delta functions, but in one of them I have replaced the k1, k2, k3 factor by p, because of the other Dirac delta function, which imposes the fact that p is equal to k1 plus k2 plus k3. That is why you get this factor. Let us simplify it further. So what we can now do is we can actually calculate, we can perform the other Dirac delta function that we have and reduce one of the integrals. We can perform one of the integrals now using the Dirac delta function. So let us perform the k1 integral. So if we perform the k1 integral, then we will get minus lambda square by 6 2 pi to the power 4. So let me write it in this way. It's better to write it in this way. Minus I lambda whole square 2 pi whole to the power of 4 delta 4 q minus p. Then we have np nq. But you can once again impose these factors, that since q must be equal to p, so you can write this as np square, right? But it is better to write it in this way, np and q. I'll tell you why. Times, now we are performing the k1 integral. So if you perform the k1 integral, what remains is if the before k2, the k2 and k3 integrals. So each of them looks like this. Before k3, you have 2 pi whole to the power 4 in each of these integrals. You write it in this way, you write these factors, so that gives you 2 pi over to the power of 8. We have performed the K1 integral, so this will give us I divided by K1. K1 is what? K1 is P minus K2 minus K3. So this gives us P minus K2 minus K3 whole square minus H square plus IFC. So this is the propagator that you get. So we have performed the K1, we have replaced K1 by the factor that you have in the Dirac delta function. Then you have I, then the other factors are as it is K2 square plus M square plus I epsilon times I K3 square minus M square. So that completes this calculation. So what we have done is we have translated the expression on top. This was the expression that we have written down at the beginning of this class, and we have written this expression now in terms of momentum integrals. And this is the final expression. So this corresponds to this diagram. So the expression for this is minus I lambda whole square by 6. This 6 comes because of the symmetry factor corresponding to the diagram. Then you have this thing, then you have these external factors. Then there are two integrals over momentum K2 and K3 and 3 factors like this. Is this okay?
Yes, sir.
Good. Now let us see. Let us write down the Feynman rules in momentum space. Let us now write down the Feynman rules in momentum space. Look at this diagram. What is the structure or anatomy of this diagram? There are two external lines, there are two vertices, there are 3 internal lines for propagators, and you can say from here there are 2 loops. Right? There are 2 loops. Why? Because this is one loop and this is the other loop. So there are 2 loops. Okay? The rules, the Feynman rules in momentum space are as follows. Corresponding to each vertex, you have to put in a factor of minus I lambda. In the position space, what it was? It was corresponding to each vertex, you have to put in a factor of minus I lambda times an integral over that vertex, over that spatial point. But in momentum space, you just put in a factor corresponding to each vertex, you put in a factor of minus I lambda. There is no integral. So there are 2 vertices. So you get a factor of minus I lambda whole square. The 6 comes due to the symmetry factor that I have already discussed. So D is equal to 6 in this case is a symmetry factor. So put in the symmetry factor of the diagram. What is this factor? Look at this factor. What is this factor? Can anyone say?
So momentum conservation term.
Overall momentum conservation. Overall momentum, because a particle with momentum P is coming and Q is going out. So since the 4 momentum must be conserved, therefore Q must be equal to P. So overall momentum conservation comes with a factor of 2 pi whole to the power of 4 delta 4 Dirac delta function. So this is the overall. So for each diagram, if you want to write it down in the momentum space, you have to put in a factor of 2 pi whole to the power of 4 delta 4 Q minus P. So this is the overall momentum conservation. Okay. What is NP and NQ? You remember earlier in the position space, it came in. Those external lines were coming in with factors of NQ, NP, e to the power of minus IQ dot y. That was the incoming particle, and for outgoing particle, it was NQ e to the power of IQ dot z. Right? So there are plane wave factors. But in momentum space, see, there are no plane wave factors. The plane wave factors are gone. In fact, this expression does not contain any position variables. there are no y and w remaining in this expression. Everything is in terms of momentum variables, right? So for the external lines, what you have to do in momentum space, the rules are just put in the factors, the normalization factors corresponding to the external lines. For this line, put in a factor of np. For this line, put in a factor of nq. So that is another rule. So vertex, each vertex minus I lambda, symmetry factor for a diagram, np for the external lines and outgoing lines. Outgoing goes with momentum q, so you put in a factor of nq. And overall momentum conservation, so 2 pi whole to the power 4 Dirac delta function q minus p or p minus q. So for this diagram, you can immediately write this term, the factor sitting before the integral. What about these loops? There are 2 loops and 3 internal lines. What about these things? Corresponding to each loop, here, corresponding to each loop, there you have to put in a integral over that loop momentum. So let us say that this P, it is like Kirchhoff's law in current electricity. So current comes in a node, gets bifurcated, you put in wires, so there are 3 paths say. So the current will be shared according to the resistance values, it will be shared Q1, Q2, Q3. The sum of Q1, Q2, Q3 has to be equal to the incoming value of the current. So just like that, it is just current distribution kind of thing. So P comes in and you say that this momentum is K1, this momentum is K2, and this momentum is K3. So these are all the momentum, the internal momentum that you have. Okay? What is K1? You can immediately write it down. K1 is basically nothing but P minus K2 minus K3. This is from momentum conservation. You can write it down. How many loops are there? There are 2 loops. The Feynman rule is corresponding to each loop. You have to put in a momentum integral. You have to put in an integral like this. So this is the loop. You have to put in a loop integration corresponding to each loop. So if I say that my independent momentum, you are free to choose what the independent momenta are. You can choose either K1, K2 or K2, K3 or K1, K3. In this case, I have chosen K2, K3 as my independent momentum and related K1 in terms of P, K2 and K3. Okay? So corresponding to each loop momentum, these are the loop internal momentum or loop momentum. You will have an integration over that loop momentum. So there are 2 independent loop momentums because there are 2 loops. So K2 and K3, so that gives you a factor before K2, B by 2 pi whole to the power of 4. We have a factor like this, and another loop integral before K3 by 2 pi whole to the power of 4. This is the Feynman rule. Corresponding to each loop, put in a factor of put in an integration corresponding to that loop momentum, independent loop momentum. So you have these factors. So that is taken care of. Now you have 3 propagators. And for each propagator, the rule is I by this. So for each propagator with momentum k, so for example, if you have an internal line like this with 2 vertices, the final rule is I by a square minus n square plus I x square. This factor you have to put. So for this propagator, you have I, and what is the loop momentum? It is K1 square minus m square plus I epsilon. But what is K1? K1 is this. So you have basically P1 minus K2 minus K3 whole square. Corresponding to this K2, you will have this factor, and K3, you will have this factor. And so we have actually managed to derive the Feynman rules in momentum space. We apply the Feynman rules in momentum space, we will get this expression without calculating anything. Is this point clear?
Yes, sir.
Are the Feynman rules in momentum space clear? Okay.
Yes, sir.
So if this is clear, then you should be able to write the expression for this as well. You know what is the expression for this in position space? How many vertices are there? Only one vertex, right? So that gives you a factor of minus I lambda. I'm writing down the expression in position space. Minus I lambda. What is the symmetry factor of this diagram? 2. Because the propagator, the two ends of the propagator ends at the same point. So that gives you a factor of 2. So divide by 2. But vertex corresponds to minus I lambda and an integration over that point. So that gives you a d4, say z. If I call this point z, okay. There are external lines. So what will you get over here? You will get np e to the power of minus I p dot z in q e to the power of I q dot z. So these are for the external lines. And what about this propagator? We get delta f 0. Actually, this 0 is basically z minus z. So this is the expression for this diagram in position space, right? And this we have already derived earlier. Just a second. Anyway, so this is the expression that you have. Now you do the same calculation. One second. Just write everything in terms of the in terms of the momentum. So what you can do is, see, in this case this is trivial to do. Why? Because this will give us minus I lambda by 2. NP will go outside. Delta F 0 also you can just write it outside. D4Z and integration over this thing, right? So that gives you a factor of 2 pi. After integration, it will give you a factor of 2 pi over to the power of 4. And then delta 4. So we perform the Z integration. Delta 4 Q minus T. So this is your expression. And in momentum space, what you can write is the following. See, delta F0, I have actually written it down earlier also. So you can write this down as integral over d4k by 2 pi whole 4 I k square minus m square plus ix. Just check. If you apply the Feynman rules in momentum space, you will get precisely this expression. Why? Because for each vertex in momentum space, the rule is minus I lambda, symmetry factor by 2. NP stands for the external lines. 2 pi whole 4 is the Dirac delta function, overall momentum conservation. And for this loop, this propagator, what you have, this propagator, this internal line, this has a loop momentum k, and for each loop, there is an integration over d4k by 2 pi over to the power of 4, and so this stands for the loop integration. Because of loop, you have this integration over the loop momentum, and you have an internal line which closes on itself. So this propagator which gives you a factor of I by k square minus m square plus I x. Because this propagator which closes on itself gives you the loop. This propagator has momentum k, and therefore you have this factor of I by k square minus m square plus I x. Is this clear?
Yes, sir.
Good. And you can now play with these things further. You can actually start writing down expressions, mathematical expressions for diagrams like this. I just leave it as an exercise for you to do. Suppose I give you a diagram like this. And ask you to draw the to write down the expression corresponding to this diagram. So you can do it. It's simple. I can also ask you to write expressions for this diagram. You can try to write down a mathematical expression for this. You should be able to do it. You can basically try to write down an expression for this diagram in the position space, and also try to write and then convert it, Fourier transform it, get the expression in momentum space, and also directly write down the expression in momentum space by using the Feynman rules in momentum space. So I hope the Feynman rules for the 5-4 theory, for this theory, are clear, both in position space as well as in momentum space. So you can ask questions. If you have any doubts at this point, you may ask me.
Sir, for the last diagram that you drew, explained, there shouldn't there be a I term in front of delta F0?
Absolutely, there is I here. Absolutely. This I stands for this. Correct. There is I here. Because for each propagator, you have a I delta F y z minus y or y minus z whatever. This I missed it. There is a factor of I here. And that I gives you this I. Any other question? So please try to write down the expressions for these diagrams and go through the rules, Feynman rules, and try to write down expressions corresponding to diagrams using Feynman rules. That will give you practice to how to write down mathematical expressions corresponding to Feynman diagrams. Just before I end this lecture, I will just mention to you about one important point. You can see that these are basically correction terms, right? These are correction terms. These are correction because you are calculating things up to first order in the coupling constant. Coupling constant is much smaller than 1, and therefore these are and therefore you are allowed to use perturbation theory. So these are basically like small. These terms should be smaller and smaller than the preceding terms because these are corrections. You are calculating. You are using perturbation theory. But let us look at this simple correction, the first order correction to the scattering process. Look at this one. Look at this diagram. The correction, the result for this diagram is this. Can you see something very interesting in this result? Can you see something interesting in this result?
A particle of momentum k suddenly appears and then disappears.
Yeah, that is because of the interaction, right? Because the particle, incoming particle, this is an incoming particle, then it does some kind of a gymnastic, then it again goes out with momentum q. But the point is that this has a loop. This loop has a momentum. This is an internal particle. It's a sort of an internal particle. It does some kind of a gymnastic and then goes out. Then again, this is the particle that goes out with momentum q. And p and q should be equal because of momentum 4 momentum conservation. Energy and 3 momentum should be conserved. But look at this integral, this loop integral that you have. d4k by this and this. How many powers of k are there in the numerator? By the way, these integrals are from minus infinity to plus infinity. So these k's can take all possible values. So at very high momentum, see that there are 4 powers of k in the numerator and 2 powers of k in the denominator. So effectively this diagram, this particular expression, if you do the cancellation, there are k square 2 powers of k on top after cancelling. 4 powers of k here, 2 powers of k in the denominator. So after cancellation, you have 2 powers of k in the numerator. And since you have two powers of k in the numerator, the integral, this k can take very large values. The upper limit is infinity for this integral. Therefore, this diagram is quadratically divergent. So this expression is quadratically divergent. And this is something very interesting, because this term that you have calculated should in principle be small, because this is a term that, because the fact that it is small, it must be small, because only then perturbation theory will work. If it is not small, then perturbation theory, if it is larger than 1, if it is greater than the preceding term, then it simply tells us that perturbation theory fails. But here, you see that this term is actually quadratically divergent. But on the other hand, you're saying that this is a correction, is a first order correction to my amplitude due to the interaction. So how can a correction blow up? So this is something very problematic in quantum field theories, that all these group integrals, whenever you have loops, these group integrals actually, it turns out that most of the times these loop integrals leads to divergences. In this case, it is a quadratic divergence. You can have logarithmic divergence and so on. So this correction term that we have calculated is not really very nice, because this itself is a divergent quantity, and one has to learn how to. So the result that simply tells us that the result that we have got from here is nonsensical. It does not make any sense because it blows up. So there is an entire program which is called regularization, and then followed by renormalization of quantum field theories. The first program is regularization. So it is a program which tells us how to make sense out of some nonsensical expressions. How to make sense from nonsense. This is the main thing of regularization, and we shall discuss these things as we move on. So how to make this expression meaningful. We will see how to do it. But I think it is a good point to stop here today. So let us carry on from this point in the next class. Okay. If you have any questions, you can ask.
Sir, does this problem also arise in the position space representation?
See, in the position space representation, you are from these expressions. See, if it arises here, it must be there also, right?
Yeah.
If
Yes.
it arises here, then it must be there also, because this expression you have actually obtained from this expression by Fourier transform. So if it is there in the momentum space, therefore it is there. So this expression is equal to this expression.
Yes.
So if it is there here, then it must be there. It basically tells you that the expression corresponding to this diagram, which is supposed to be a correction term, so it is supposed to be small, is actually divergent in itself. That is what it says. That makes quantum field theory very problematic. But fortunately enough, there are methods by which you can overcome this problem. And the program by which you can overcome this problem is called the program of regularization, and then followed by renormalization. It is very important for a field theory, for a quantum field theory, to be renormalized. If it is not renormalizable, then it becomes really problematic, because then you will understand later that if the theory is not renormalizable, then it is not a very good theory. You cannot make predictions. You cannot predict things from that theory. because you can make certain, you can predict things. It is not that you will not be able to make predictions. For example, there are theories like the 4-Fermi theory in beta decay. This is a theory which is not renormalizable. The 4-Fermi theory is not renormalizable. But it is not that you can, whatever results you get from there do not make any sense. At tree level, the result, all the 4-Fermi theory is perfectly fine. But once you start trying to calculate corrections, then you fall in a problem. You fall in a trap. So you cannot calculate corrections. But at tree level, the leading order term, 4-Fermi theory is perfectly fine, even though the theory is not renormalizable. So if the theory is renormalizable, the added advantage is that you can start making predictions, and those predictions you can rely. Those are reliable predictions. So if a theory is not renormalizable, then you cannot actually, you can make several predictions, but all of them are not reliable. So it is basically like effective. There are certain things in field theory like which are called effective theories. So it works in a particular energy regime. You cannot extrapolate or take that theory to higher energies or something like that. So that makes it a problematic thing. So these are like effective theories, which are, you know that this theory works in this energy regime. So renormalization for that theory is not necessary. But we'll see theories for which you can prove that the theory is renormalizable up to all orders in perturbation theory. And therefore, you can make very good, reliable predictions from the theory. Okay, let us stop here.